Welcome back to our lecture on machine translation. Today's lecture is about adaptation. So we will obtain better translation quality when the system is adapted to a particular task. So this typically takes the form of domain adaptation to a specific domain, for instance, information technology. Some of the training data might be more relevant than others to do well on this task, but we might also adapt to a specific user, so personalization, or we might optimize for a specific domain or even sentence. Maybe a good example for information technology is the word window might mean something completely different in a normal conversation, especially talking about architecture or houses, than when we talk about information technology, where it's usually is the name of for a particular piece of the screen that is dedicated to a specific application. So let's first talk about domains. It's a somewhat ill-defined term, as we will realize. So the actual practical definition is a collection of text with similar topic, style, level, formality, and so on. So practically, however, this means it's a corpus that comes from a specific source. So we have different sources where we can get our parallel corpora from, and then one source that constitutes a domain. Here is an example. If you go to the website Opus, that is probably the best reservoir of parallel corpora for many, many languages. Here are the corpora they list for Italian, English, and so you can go down here the list of there's open subtitles. So this is a collection of user-generated translations of movie and TV show subtitles. Then there is EU Bookshop. These are official publications of the European Union, and so on. So in terms of domain, you could say the first one is kind of subtitle, movie domain. The second one is more formal, government. But really the definition of the domain is where the data comes from. And this might be, for instance, fairly fine-grained. So here, for instance, you have open source documentation for the GNOME user interface, while here you have uh, localization files for the KDE4 desktop environment. And they are quite similar, but since they're now here separated out, they can actually be viewed as two different domains. To give you some sense about differences in corpora, here are some examples. So here is what I'm now calling medical. Actually, if you look at the previous slide, I don't think it exists for Italian, but it would have been called the EMEA corpus from the International Medical Association. Okay, so here's the example text. Abilify is a medicine containing the active substance. I don't even know how to pronounce that. It is available as 5 milligram, 10 milligram, 15 milligram, and 30 milligram tablets, and so on and so on. So it has things in parentheses, a lot of measurements, and absolutely unpronounceable names for things. Then you have software localization. So this is to a large degree what it actually is shown to a user in a user interface. So it has short things like default GNOME theme, OK, people. So think about all the things you encounter when you view an application. There are obviously many short text snippets that show up in menu lists and so on, and there's different options. Then there is literature. There was a slight noise behind her, and she turned just in time to seize a small boy by the slack of his roundabout and arrest his flight. So that is declarative language, grammatically well-formed, tend to be maybe longer sentences, although that really depends on the literature. It has often fairly broad vocabulary, definitely more broader vocabulary than spoken language. and it also tends to have much more emotions in it. Then there is law. Okay, so here you have curriculum to the interim agreement with a view to the European Partnership Agreement between European Community and its member states of the one part and the Central Africa Party on the other part. So this is, yeah, very formal text, a lot of complicated names for things. You have all these grand noun phrases, economic partnership agreement, and so on. Also, then things become not just generic. You mean talk about member states in general. These are capitalized, so you're talking about the very specific member states of the European Union. Okay, then we have religion. So here's the text for that. This is the book Free of Doubt and Involution, a guidance for those who preserve themselves from evil and follow a straight path. That again is, it's more similar to literature in that it's well-formed sentences, although it tends to have more archaic names for things and also has definitely a much more narrow subject matter. So I'm not sure if you know what involution means. I don't. But it's probably in earlier versions of the Bible. So then there's news. The Facebook page of the leading Iranian leading cartoonist Mana Nayeshna was hacked on Tuesday, 11 September 2012 by pro-regime hackers who call themselves Soldiers of Islam. So again, these are long, well-formed sentences, a lot of names that are otherwise not occurring tend to be declarative sentences. There's not a lot of I and you in there. There's not a lot of questions in there. But things like names and country dates and country names and so on. Okay, movie subtitles. So we're taking you to Washington, D.C. Do you know where the prisoner was transported to? Washington. Okay. So this now has questions. It has things like you. It has also a lot of short utterances and then casual languages. So we're taking, that's not what you would be writing in a newspaper article, these kind of contractions. And finally, you have here, a final example here is Twitter. So thank you Starbucks and Spotify for celebrating artists who give good with a donation to BTV Foundation and to great organizations by Metallica and Chance the Rapper. Limited edition cards available now at Starbucks. It has shortened sentences, so limited edition cards available now at Starbucks. Really should be are available now at Starbucks stores. So some contraction, so some omissions to make it shorter, but then of course the glaring thing is it has all these kind of very bizarre Twitterese identifiers of other Twitter users or these hashtags that denote a theme. Here's also an artifact of shortening something. And this is actually a relatively well-formed sentence for Twitter. Twitter is also notorious for having a lot of spelling errors or just, intentionally creative spelling. So let's get a bit more analytical about this and think about the dimensions of domain. So the first that comes to mind is topic. What's the subject matter of the text? Is it politics? Is it sports? Is it lifestyle? The next one is modality. So how was the text originally created? Is it written text or transcribed speech? And if it's speech, is it a formal presentation or informal dialogue full of incomplete and ungrammatical sentences? I think in written text you can also distinguish between, is it like a formal, did it go through a formal authoring process with reviewing and editing, or was it just kind of slapdash put together at a more of a moment at 3 in the morning? Then there's register, which is the formal name for basically the level of politeness. So that is reflected in the kind of language you use, but in some languages it's also very explicit. So for instance, in German there is 2 words for you, one informal and one formal. And the informal one is only used when you talk to friends or children, while if you meet any other adult person that is not your friend, you call them Z. And there's actually a somewhat etiquette around when you move from calling someone Z and someone Du. That's kind of a firmly established step of friendship. Although these distinctions are actually eroding a bit. So in an academic environment, you would probably say Du to a lot of people. Okay. But there was also a time where children had to talk to their parents as Z instead of Du. So there's a two level of politeness. A lot of other languages have that too. French and Spanish and Portuguese and so on. And there are other languages like Japanese who have fairly regimented levels of politeness. Okay, so intent is the text, the statement of fact or attempt to persuade or communication between two parties. So that definitely is also reflects how it is written. Does it kind of make appeals to people? Or is just kind of the language that's being used is just formal statements of fact? Or does it have things like should or may and so on? And finally, style. So that's a very broad term. And here I'm just kind of listing as, is it emotional or flowery language, or is it very terse and informal? But there are obviously many, many aspects of style. It's the kind of language to use. Do you use more kind of up-to-date recent language? Do you use like the latest hip jargon, or how the kids speak? Or do you use kind of more archaic language intentionally, as we've seen in a religious text? All that impacts style. You use short sentences, you use simple sentences, and so on. So, so given these dimensions, we in reality don't actually have any real information about them. So it's not like we getting parallel corpora that are labeled according to the dimensions we just laid out. So let's think, for instance, let's take a corpus that is extracted from Wikipedia, a very popular source for text, because it spans a whole range of topics. And it's actually fairly consistent in modality and style. So in modality and style, you can maybe define it in topics. You can't because it really covers everything. So let's say you have a practical goal in your machine translation system. You want to enforce a certain level of politeness. You want to make sure that it output text that has a certain level of politeness. Maybe it wants to be very polite or just wants to be as casual as possible for various reasons. Maybe it's a chatbot. You want to be more casual. Maybe it's more like formal announcements. You want to be more polite. So what can you do? You can say, well, the European Parliament proceedings are probably more polite. So that's our evidence of a corpus that is polite, while movie subtitles are probably less polite. So there's a corpus that is indicative of less polite. So if you want to build a machine translation system that's more polite, it should be more geared towards European Parliament proceedings style of text. So we should put more emphasis on that corpus. So the impact of domain, the most obvious thing that always comes to mind, and I already gave one example of that with the word window, but here's another example with the word bat, which means one thing in baseball. It's the thing you hit the ball with, and it means something completely different. And when you talk about wildlife and animals, then it's this kind of mouse that has apparently grown some for the summer wings and is flying around. That's one thing. So that's very glaring. And from my experience, that is actually less of the impact of domain. What is much more common is that if you move from one domain to another, that the style changes. And it might be as blatant as here. There's a difference between saying, "What's up, dude?" and "Good morning, sir," although they essentially mean the same thing. Only one would be appropriate in certain contexts. That's very blatant, but it might also be very subtle about kind of what adjectives you use. Do you use short sentences? Do you use long sentences? Do you use kind of all these various aspects of style that come in play. And adapting to a domain is to a large degree kind of figuring out what is the proper style of text. There are often multiple words that mean exactly the same thing, and picking the right word that is appropriate for the targeted style is not easy. Okay, so it's a diverse problem. So the data we may have may differ narrowly or drastically. So the parallel corpus collection I showed you, that is corpora that have fairly drastic differences in in domain and all these characteristics as we defined it. But you could also think about, European Parliament proceedings, some news commentary text, and so on. They're all kind of newsish, they're all kind of political, so they're not as different from each other. So the amount of relevant and less relevant data may differ. So you want to target a system towards a very particular task, and there might be a lot of relevant data for this task, or there might be very little relevant data for the task, or maybe not even existing data for the task. The data that is given to you may already be split by domain, so there might be very clearly different files. Here's this corpus, here's that corpus, here's that corpus, or everything is mixed together. You think about, for instance, Wikipedia as, it's somewhat mixed together in terms of topics. So if you want to build a system that is very good at medical translation, Wikipedia doesn't provide you a nice split in between the documents that talk about medical content and those who do not. The data might also differ by quality. That's a whole other bag of worms. So what is actually well translated content and what is badly translated content? Each corpus that you have may be relatively homogeneous and heterogeneous, and you may have to adapt on the fly. So that's another challenge. So can you adapt the system to a user in real time? So there's many different methods, and you may use some of them for your situation, some don't, but you often have to do a lot of experimentation to figure out what's the right thing to do. So let's first start with a kind of scenarios. Here's the multi-domain scenario. So the idea is you have some sports data. So this is your indication of the parallel corpus you have, and with that you can build a sports model. Then you have finance data, and you can build a finance model, or you have law data, and you can build a law model. So multiple collections of data, clearly identified, and you can train specialized models for each domain. And then when a sentence comes around, so for instance you have a finance sentence, you then route it to the finance domain. Or you could say, well, this sentence is kind of 80% finance and 20% sport. So for instance, it might be a sentence about contract negotiations of a football player for the next season. Then you can also do probabilistic assignment. And we'll figure out how to do with that. Okay, the other scenario is just much simpler, where we just say there is one particular targeted domain, and that's what we call in-domain data, and then there's all the rest. And the typical scenario is that you have small amounts of in-domain data and large amounts of out-of-domain data. If you have large amounts of in-domain data and small amounts of out-of-domain data, it's probably best to just ignore the out-of-domain data. So the real challenging scenario is if you have exactly this here, small amounts of in-domain data and large amounts of out-of-domain data. So you need to balance these data sources. So why should you use out-of-domain data at all? So the in-domain data might be much more valuable, often strikingly so. Having small amounts of that might be 10 times more valuable than out-of-domain data. But you still have gaps. So if the in-domain data may not have certain words that need to be translated, but it exists in the out-of-domain data, so that's some information you want to use. Or the word that you want to translate occurs in your domain data, but not with the correct translation. So it might occur once or twice in your domain data, but again, it's a ambiguous word, might have multiple translations, and the out-of-domain data might have more evidence for that. So the motivation really is for the out-of-domain data to fill these gaps, but then also to be careful not to drown out the in-domain data. There was a study almost a decade ago by a workshop that actually happened here at Johns Hopkins University, where a deep dive into domain adaptation was taken in the context of machine translation. And they came up with a taxonomy of adaptation effects. And they all started with S, so it's S4 taxonomy of adaptation effects. So seen errors, so what to do with words that have never been seen before. Then sense errors, words that have been seen before but never used in this way. So maybe a monitor is maybe seen in news data as you're monitoring activity. Some monitor was put in place. Well, in technical, it's a word for computer screen. Then score data. So this is the problem where you move from one domain to another, and in one domain it prefers one translation, but in another one it prefers another translation. So for instance, the word manifest might have a preferred meaning in news and a different preferred meaning in medical. They might both occur in these corpora, but the preferred meaning is in the narrow domain. That's the one where we actually also take our preferences from when we actually translate that medical content. And then finally, search errors, where all the models point you to the right direction, but you have mistakes in search. So they basically analyze a lot of effects of if you train on domain and out of domain, how do these different errors show up? Okay, let's take a look at one example how a general domain model might differ from a specifically trained in-domain model for chemical patterns. So here's the German source sentence, so Verfahren und Anlage zur Durchführung und so weiter und so weiter. And you have the human reference translation, so method and system for carrying out an exothermic gas phase reaction on a heterogeneous particle catalyst. And you see here the general translation model struggling with that. So procedures and equipment, okay. For the implementation, that's definitely the wrong word, of exothermic that is not even translated. And then you have response here twice. So it's just generally having a hard time with this type of material. So both in terms of maybe using some words that are not the right translations for the German words, and some having to do with just being unused to this kind of jargon. And the in-domain model translation here has method and system, which is exactly what the reference translation is for carrying out an exothermic gas phase reaction on a heterogeneous particle catalyst. So this looks like almost perfect translation. So the differences here are stylistic, so method and system versus procedures and equipment, where methods and procedures probably is pretty synonymous, but in patent domain you have a method has a very specific meaning, so you use that word there, and system also has a very specific meaning, so you use that term there. And then word sense with between catalyst and catalytic converters. And then just generally better language coverage, that it knows terms like exothermic gas phase reaction versus here, where it struggles both with the translation of this word here and then kind of duplicates this word for no good reason at all. Okay, so let's move over to solutions to the problem of building very targeted domain models for kind of very targeted task-specific machine translation solutions. The first thing you want to look at is mixture models. So the default solution is to just combine the data we have. So we have a lot of out-of-domain data, and we can combine that with small amounts of in-domain data and then throw it all together. The problem, of course, is this is going to be too biased towards the out-of-domain data. So the out-of-domain data is much, much larger than a little bit of in-domain data you have. So the first obvious solution to that is to just oversample the in-domain data. Let's throw it in 3 times. So the in-domain data is now weighted more heavily than the out-of-domain data. And in the final training, they kind of balance each other out more nicely. You can do this on the data side. You can also do this on the model side. So you can train a model just on the out-of-domain data and a model just on the in-domain data, and then combine their predictions. Think about the ensemble decoding methods that we talked about during decoding. So each of these models makes predictions, and you can just give a preference to the in-domain model's prediction somehow. Another solution is to just at training time make the training algorithm aware of what domain particular training examples come from. So generally, we're going to train a model on all the domains, so we concatenate all the training data together, but then we indicate the domain for each of the input sentences with a domain token. So we're going to basically append a token. It might be something like this here, where you put sports in all caps and brackets around at the beginning of each input sentence that comes out of the sports domain. So you label the training data this way. So it will have seen sports sentences labeled with that. And then at test time, when you say this is a test sentence that also is from a sports domain, it can associate that with what it's seen in training. So think about this, how this works in your machine translation system is the domain token will have a word embedding. So there will be one additional word embedding in the input sentence representation. This is the embedding of the domain. So it's kind of a domain embedding. And then the attention model will rely on that as needed. So the attention model can then put varying amount of attention on this domain embedding, and then take that as a factor to influence its decisions about how translation will proceed. The domain might also be unknown at test time. So if you have a test sentence come in, someone might tell you this is a sports sentence, please translate it as a sports sentence, but it might also be not classified by domain. So you can then build a classifier that predicts the domain of an input sentence and then predicts the domain token. Therefore, we're going to add that domain token as an additional input. There are also efforts of considering that as a soft decision. So if the classifier says, well, it's probably 70% sports, 20% law, and so on, you can then put in either multiple domain tokens or have a soft domain assignment in the vector. So you said there's going to be a domain embedding vector. So you don't have to feed that in as a one hot vector, but as a kind of relative count a vector as input. So this might also be used to label training data that is not labeled for domain. So we can push domain adaptation even further. The idea of having a personalized translation system. So the most typical scenario for that is if this is a machine translation system that is used by a professional translator to aid them with their work, but they also want the machine translation system to pick up their particular style of how they write things or their particular domain of subject matters they typically work on. So the machine translation system should be optimized for that. You can also take it from the data side, where maybe you want to optimize the machine translation system for a particular author, if you think about literature translation, or particular speakers, when you think about translating the speech of politicians, maybe you want to then optimize it for the way a particular politician formulates things and phrases things, and do as accurate job as possible for that. Obviously, for these, the domain token classification idea doesn't scale very well because you're just going to end up with way too many of these domain tokens. And there's also very, very little for each of these, what we now call domains, which is, for instance, just text translated by a particular translator or text authored by a particular author. So these are relatively tiny amounts. Here's a solution for that. So this is the method I proposed for personalization. So the key idea here is that we're gonna leave most of the model unchanged. So it's just a general translation model, and the domain-specific part here, or the personalization-specific part, is the word prediction layer. So only at the word prediction layer step, we're gonna then factor in the domain. So if you remember, so previously we did word prediction in a way where we considered the decoder state, maybe the previous word embedding, and the input context. So this is now a recurrent neural network setup. So these are the two things that come in there. So these are the states that combined, multiplied with additional weight matrix, and a bias vector. So now the idea is we're not going to just do this here where we have this calculation with a bias vector, but to also add an additional bias vector that is specific to particular person P. So it's not personalized to person P, so we're going to learn additional bias vectors for particular person P. So we're just going to prefer their word choices. May it be because of their particular personal style, or may it be because the subject matter they translate technical domains, so Windows always means something else, so particular translations show up more often than others. Okay, let's look at topic models. So there's been a long history of looking at natural language text and documents that occur, and recognizing that they cover a lot of different material to then break them up into topics. So the word topic here is used almost analogous to the way we use domain so far. The topic is always used when we have this automatically detected topic segmentation, typically by algorithm like Latent, Dirichlet Allocation. So the main idea of this is that given that text covers all kinds of different topics, can we kind of group it into these different topics? Can we then identify which topic a particular text comes from? So the algorithm that is being used for that is most commonly latent Dirichlet allocation, the LDA. So this is formalized as a graphical models. The idea is that sentences belong to a fixed number of topics, and then the model predicts the distribution over topics and predicts words based on each topic. So it has a very nice illustration then where we can pick up for particular topics what are kind of the most prominent words for these European political party interests. That's one area of topics, and crisis rate, financial, monetary, that's maybe another topic. So the first one is more political, the second one is more financial. But since they're automatically detected, they don't come with nice names like political and financial, but they can be fairly readily identified by just looking at the most prominent and indicative words for them. So we can also drive down the notion of topic all the way down to the sentence level and think about sentence embeddings. So basically the idea is that we have to represent sentences somehow with a unique vector. The simplest method is to kind of compute an average of embedding of the words in the sentence, but there's also ongoing research on more complex methods we will actually encounter in some of the future lectures as well. But then the idea is they can cluster the sentences into topics. So this could be things like k-means clustering or randomly generated centroids, and then assign each sentence to its closest centroid. and then recompute the centroid as the center of the embeddings of its assigned sentences and iterate. To give you a quick idea how this works is, so you have all these sentence embeddings, and you first say, okay, we're going to pick one of these things as centroids, and then say, okay, this is the one cluster, this is the other cluster. And then you look at the clusters and say, well, the kind of more central point to this cluster is probably not this one here, but maybe more this one or that one. And then readjust the clusters, and then you get a different centroid. So you automatically kind of cluster sentences by the similarity. So when an input sentence is to be translated, you can assign a topic based on the proximity to centroids and translate it with this topic-specific model that emphasizes this particular subset of sentences. Okay, let's now look at a different group of methods under the headline of subsampling. So here's the basic idea, that you have a lot of out-of-domain data and you have in-domain data, but a lot of the out-of-domain data is really not that relevant for our task. So why don't we just subselect the sentences that are related to our in-domain data and only use those for training? So we throw away most of the out-of-domain data, maybe because we really have large amounts of out-of-domain data, and just pick out from the out-of-domain data the sentences that are actually relevant for our particular translation task. There are various methods. There are two different goals you have in mind. The first one, with the goal of looking at out-of-domain data, is really to increase coverage. Is there certain words or phrases you don't have translations for or not sufficient translations for, but they do exist in the out-of-domain data? Then we should use pull out those sentences that fill these coverage gaps. And the other goal is, of course, to not then get distracted from the correct translations we find in our in-domain data and get content with the same in-domain content and style. The kind of standard method that has been pretty firmly established at this point is called Moore-Lewis. So the idea here is that you build language models. So you build two language models, one on all the out-of-domain data and one of in-domain data. And then you can look at each sentence and score it with the out-of-domain data and the in-domain data, and figure out, is this a particular sentence that is preferred by the in-domain data or by the out-of-domain data? That's most similar to the in-domain data, or the out-of-domain data is preferred by the language model trained on the in-domain data, or the language model trained by the out-of-domain data. Mathematically, this is put down to what's the probability that this particular sentence is assigned to with our in-domain language model, and look at the probability that the sentence is assigned to with out-of-domain language model. And we prefer the sentences where the in-domain language model gives it a relatively higher score than the out-of-domain language model. So what's trying to be indicated here, maybe this sentence, the green model likes very much. So it's more a green sentence. So we go with that. And that is then a method to pull out the most relevant sentences. So modified Moore-Lewis is the variant of that, where you do this with language models both trained on the source side, on the source language, and on the target side, on the target language. This can also be done with subsampling it down to replacing some of the words with part of speech tags. The language models often give them really, really bad scores for things like points, because this may not have occurred in domain, but has occurred out of domain, and then gives it unreasonably better probability in the model where the word occurs in. So maybe you can just replace all that with tokens like here, proper noun. Um, so there there has been work where this was done pretty radically, where really most of the vocabulary was replaced with part-of-speech tags, and it even shown to be working better than the previous method that operates on words, which really raises the question as how much domain adaptation is a matter of just adapting to style. So the style is clear from kind of just the sentence structure, kind of the sequence of part-of-speech tags, and not the terminology. Okay, so one problem with this method I just proposed, it's really just geared towards sentence pairs that are strongly in domain versus sentence pairs that are not at all close to the domain, but we're basically going to pull out sentences that we are very similar to the training data we already have. So we might not learn much from them. So not much new is added this way. So one of the original goals we had was also to increase the coverage with out-of-domain data. So we also need coverage-based selection. So here's the basic idea. So you score each candidate sentence pair to be added based on a word-based score. So you're going to have some score for each word in the sentence. And a simple word score is check if that word already occurred in the previously added sentences. So you already have some sentences added, all the words, either words occur in them or they don't occur in them. And then when a new sentence comes around, the question is, should I add that to my training data? And the question is, well, does it contain words that have been seen before? And does it have many words that haven't been seen before? And then I prefer the sentences that will be added that has the highest score, and this particular simple score scenario, sentences that have a lot of uncovered words. You can do this on words. You can also do it on n-grams. So this is just kind of spelling it out over n-grams here. So the second sum here goes over all the words, while this one goes over n, the size of the n-gram. And another way to do it is to not just go by 0-1 scoring, where you say, did it occur once or did it occur never, but also say, well, if it occurs once, we might still want to get some more data about it. But if it occurs 1,000 times, I don't really care anymore. So the idea is to do feature decay. So we basically have a frequency and we just kind of pass it to the exponential function to kind of reduce the preference for words that occur really, really frequently. Okay, so far the question was pretty much either we include a sentence pair or not, but now we might also want to consider can we weigh sentence pairs based on relevance. So instead of having this hard decision of what are we including certain material in our training data or not, to now say, well, we include the sentence pair in our training data, but it's less relevant, so somehow we're going to discount it. So we're going to use the same kind of scoring methods that we've done previously for filtering, except we're going to now include all sentences and just keep the score around. So the simplest way to do this is to scale the learning rate by the relevance score. So while we do training and we come across a sentence pair in training that was scored relatively low, let's say it got only a score of 0.1, where 1 would be given to in-domain sentences and 0 would be the lowest score you can assign. So 0.1 is a relatively low score. That when you then do your gradient updates and apply, first of all, the learning rate, you can now also apply an additional learning rate that includes this number 0.1 as a factor, and then basically discounts updates from out-of-domain sentence pairs. Okay, now the final set of solution, which is really the most established method these days, is fine-tuning, which has some benefits and some disadvantages over the things we just talked about. So here's the idea. So you have first all the data or just the out-of-domain data and train a big model. And then you have a second training stage where you take that model and just train on only the in-domain data for a while and then have an in-domain model. So you first train on the out-of-domain data or all available data and then stop at conversions as you usually would do. And then you continue to train on just the in-domain data. So you first let it learn everything it can possibly learn about all the vocabulary and all the phrases. And then you shift towards training where it kind of moves towards more the in-domain data. One problem with that is called catastrophic forgetting. So if you overdo the fine-tuning, it might overfit to the in-domain data and forget everything it's seen before. The previous training stage really acts similarly to random initialization you do in normal machine translation training. So at the beginning, you would just randomize all the parameter values and then start training and get good training weights. Now you start with this out-of-domain model. And well, what stops you from, if you only expose the in-domain data, pretty much forget everything that was in the original parameter settings. We really have two goals. Yes, we do want to do well on the in-domain data, but we also want to maintain quality on the out-of-domain data. This is for two reasons. A, because maybe we want to be generally more robust on sentences that are not completely within the very, very narrow in-domain data range you care about. Or we also maybe want to do well on sentences that kind of are more unusual and are not super representative in the in-domain training data. So one idea is to update only some of the model parameters, to not just be able to let the model kind of replace all parameter values, but only some of the parameter values will be adapted during the adaptation stage. So this is generally because we have maybe too many parameters and too few in-domain data examples. So the idea is to update only some of the parameters. Maybe, as we've already seen, maybe just the outward word prediction softmax. That's what we already saw in the personalization example. Maybe just the weights for the decoder state progression, or maybe just the output word embeddings. So the idea is what's probably most relevant for domain producing output and Dirichlet domain is the decoder part, the prediction part, not so much the encoder part. Here's another idea where the idea is we actually leave the general model parameters fixed, and then we learn additional set of parameters for the in-domain data. And what these additional parameters is, they only scale values in the original model by a narrow range. So let's look at this formula here first, where we look at the state, the decoder state, and usually this is the decoder state, and now the values in the decoder state get adapted with this additional factor, and this additional factor is going to be something that ranges between 0 and 2, so it might zero out values, it might double values, but otherwise it doesn't completely change them. So how do you keep the values in the range of 0 to 2? Well, with this kind of formula here. So if this is your parameter, and if you apply this formula, this ensures that the values are only in the range between 0 and 2. So if this here goes to infinity, this becomes close to 0, and if this goes to 0, then this becomes, the overall value here becomes 2. And the nice thing about this is something that can be turned off and turned on at will. So you can have also several of these sets of parameters for different personalized domains. And finally, here's a method about called the regularized training objective. So the stated goal is we don't want to diverge too far from the original model. So the original model has something useful in it. We don't want to forget everything there. So we don't want to get too far from it. So we want to adapt towards our domain, but we don't want to stray too far from the original model's predictions. And this is explicitly then used here during training. So the default training objective is, just as a reminder, it predicts output words at each given point in time, at each time span that it predicts a probability distribution of the output words, and then the feedback to the training is how much probability did it give to the correct word y. So it gives different probabilities to words, and the probability it gives to the particular output word y that is at time step I, that's your cost. So that's what we're going to pass through as cost as for backpropagation training. Now the idea is, we're going to keep that cost, so we're sticking with that, but we also include how much did our original general model that we have predict this word. So if our original model says, that was a high probability word, then our new model should also say this is a high probability word. So we're going to combine those two cost objectives. So these are the two training objectives. One is the cost as we usually do it, and now we have this regular training objective which says how much did the original model predict this and how well does it match our current model's prediction. So there's a hyperparameter alpha here that we can use to balance in-domain and out-of-domain quality. Okay, let's just finish this up with some consideration of how this might play out in practice. So here's a scenario where you have a human translator in the loop. So you have a machine translation system and a human translator, and they both collaborate to build translations. And the way they collaborate is, there are many ways to do this, but the simplest way is the machine translation system provides its draft translation that then is corrected by the human translator, and then that is fed in as additional training example for the model, and then the model can take all these training examples and adapt. We'll talk in a future lecture about computer-aided translation, how to do this a bit smarter, and other methods in this area. But the idea here is that the translator kind of provides additional training data, the translated sentences that it corrects, that he or she corrects, and then that is used to incrementally update the model. So you can then use any of the methods we discussed so far to kind of retrain the machine translation model on this added data, and can maybe even do it on the fly. So another idea is to do a sentence level adaptation, so to adapt the model to each sentence that is to be translated. There's a whole range of methods that go about finding the most similar sentence in the parallel corpus. This is called a fuzzy match and has a long tradition in tools for human translators. So you're going to retrieve that and its translation. So maybe the sentence you have to translate already was translated before, or maybe it just differs by, a different date or just a different brand name or something like this. But otherwise, almost the identical sentence was there before. So you retrieve that in its translation. So that translation is really the best roadmap how to translate the current model. And then you can do various things. You can adapt the model with a sentence pair, but there are also other methods of feeding it in as additional input and conditioning context. There are various methods that are applied to that idea. Finally, let's wrap up with taking a quick look at curriculum training, another methods we will visit again in the future. We basically have the following problem, that we have in-domain data and we have out-of-domain data, and we originally said we're going to do fine-tuning, so that seems to indicate two stages. We already have the problem, how many epochs should we train at each stage, but we can make the problem even more complicated by saying, well, we start with all the data, so this is our original stage, and then our subsampling techniques tell us, well, only half of the data is really super relevant, so maybe we should focus on them. And then we can say, well, a quarter of the data is even more relevant, And then maybe only 10% of the data is super relevant. So what should we adapt to? And the answer is, well, why don't we adapt in stages? So first have a model here, then you have a model here, and you have a model here, and then you have a model here. So you have 4 training stages, and then the question is, how long should we train on them? Should we train equal amounts or less amounts? And this is called a curriculum. So a curriculum is, just consider a school curriculum. You first learn, for 3 weeks adding, and then for 2 weeks multiplying, and so on. So this is like how lessons are passed on to students. And here is how training data is presented to the machine learning algorithm. So the curriculum decides how long the training algorithm has to spend time in the somewhat relevant data section of the training class. Okay, and that's how far I wanted to take it today. And we're going to look at another aspect of data in machine translation in our next lecture, where we're going to go beyond parallel corpora. So I'll see you there.